Please welcome to the stage Senior Principal Scientist at Amazon Web Services and Professor Emeritus at the University of Maryland, Dr. Michael Hicks.
Hi, everybody. All right, so I'm a Senior Principal Scientist at AWS, and today I'm going to tell you a story of how Amazon made the dream of proved correct code a reality. So back in February of 2024, we launched a new implementation of the authorization engine that's used by all of AWS. It's part of the most security critical and heavily used code in our cloud. What made that launch special? The engine was built with formal methods, which we used to prove that the code did what it was supposed to do every time. And that code performs authorization. It's a critical function of identity and access management, IAM. You use IAM's control plane to specify who can access what in terms of your AWS account. And you write policies to control access to AWS resources. So you can think of IAM authorization as like the beating heart of AWS. It's in the circulatory system carrying AWS requests and responses. Those messages always go through the IAM heart. So for example, suppose a customer wanted to access one of your S3 buckets, that simple storage service that Kathleen talked about. The request is going to go through that beating heart built into the S3 API to decide if it should be allowed. So in particular, the S3 API contains an IAM authorization client library, which takes the details of the request and also the relevant policies to make a decision. Considering these things, the authorization engine decides to allow or to deny the request. And this engine, deployed to all of our customers, was built and proved correct with formal methods. So why did we do it? Why did we build this new engine when AWS had been operating with its existing authorization engine for more than 10 years? It seems like a lot of trouble. Well, the first answer is that we're security obsessed. It's in our DNA to continually raise the bar for our operation. Formal methods proof gives you, our customers, the highest assurance that we're correctly evaluating your policies and protecting your resources. And the second reason is that we're customer obsessed. We want to continue to make changes, including optimizations and new features to IAM to better serve you, our customers. But of course, we want to do it with confidence and with great speed. And formal methods allows us to do that, because as we make those changes, we can quickly prove that they still adhere to our specification, to what the engine is supposed to do, and do nothing else. One of the things we did right away after deploying the new engine was make it go faster. So we proved correct optimizations to our authorization algorithm. And you can see here at the time of deployment that the time it took to authorize a request improved by as much as 3 times, all across the spectrum from the slowest requests to the fastest. And we would not have had the confidence to make these changes to a piece of software that's being run 1 billion times or more per second if we did not have formal methods backing us up, assuring us that those changes are really going to be correct. Now, this authorizer is not the first time that AWS has gone to the formal methods rodeo. We have applied formal methods to a wide variety of code bases, including crypto and security code that we use, OS and low-level code, AWS services like S3, one of our flagships, and many others. One of those others is one that I worked on personally when I joined AWS back in 2022, after I transitioned away from being a full-time professor. Cedar is an authorization policy language. It's similar to the policy language that you might use in writing policies for your AWS resources, but Cedar is intended for customer applications. Where IAM is about AWS principles, actions, and resources, Cedar is about customers' principles, actions, and resources. We wanted to provide a language that made it easier for customers to build authorization in their applications. So Because we had learned the lesson from IM, we decided to use formal methods in constructing Cedar, and we did that from day one. And because Cedar is open source, you can check out exactly what we did for yourself. In the rest of this talk, I want to tell you more about formal methods and how it reached the point that it is today, where a large tech company like Amazon is able to use it to build its most security-critical and highly scaled services and code. And hopefully by the end, you'll have a little bit more confidence that maybe you can apply these techniques too. So stepping back, what is formal methods? I'm going to give you a professor's definition of it. It consists basically of two parts, and here I'm talking about the highest assurance form of formal methods. The first part is the specification. It's going to define the behavior in a formal way that your customers are relying on. It should be readable and maintainable. The second part is the implementation. Now, this is the real code that's going to run and implement that behavior. So obviously, it's executable, and you want it to be efficient. And what makes formal methods is that I can prove, using formal methods, that the implementation truly does match the specification. Now, if we dig in a little bit, we can see that the specification has usually two parts. The functional part, which describes what happens, what is it that the system is actually doing? And the second part is properties of that functional system. What are invariants that should always be satisfied during its operation? For example, security properties. Maybe that public information never influences highly sensitive operations. The proof then goes from the implementation, the code that implements the functional behavior, to the functional specification, and then we prove properties about that functional specification. So we've been throwing this word proof around quite a bit. I want to dig in again, be a little pedantic about what we mean by that. What exactly is a proof? So a proof is just a logical argument that a claim is true. And you surely have had an interaction with proof when you took high school geometry and you learned about the Pythagorean theorem. So but the Pythagorean theorem says that the sum of the squares of the two sides of a right triangle equal the sum of the length of the hypotenuse. So if we were to carry out a proof of Pythagoras' theorem, it might look like this. And actually, I asked ChatGPT to produce the proof for me. I checked it to make sure that it was correct. So you can see that in this proof, there's no mention of any specific triangles. There's not 1,000 triangles or 10,000 triangles that we're making an argument with. Instead, we're referring symbolically to elements of those triangles, features that hold over things, whole categories of things that satisfy certain properties or invariants. In other words, the argument is symbolic. It doesn't refer to particular right triangles. It refers to classes of things as it takes steps reasoning from one thing to the other until it finally comes to its conclusion, which gives us confidence that it is a universal property. It holds for all right triangles. Now, this idea of universal properties is, of course, attractive for a highly critical piece of software like the IM authorizer. So what properties might we care about in that case? Well, we can look in the documentation online and we can find this statement. An explicit deny in any policy overrides any allows. That's a universal property. It's saying for all policies, whatever set of policies you might have, if there's an explicit deny in a policy, then any other policies you might have that have an allow in it will be overridden for requests that match the denying policy. And I want that to be true for all requests and for all sets of policies. So let's call this property deny trumps allow. And let's step through it a little bit pedantically again. For all policies and requests, if there is a policy P in the policies and a statement S in P, and the effect of that statement is deny, and S matches a request, then when you evaluate the request, the result of that evaluation is deny. Now, stepping back, you might ask, why is this property important? Why is it something that we should go to the length of trying to prove that it's true? And the reason is that it enforces safety by default. Notice that when a user has explicitly decided to deny access to something, that denial always takes effect. No matter what else someone else does, adding new allows policies, for example, we're always going to deny. So this is a safer alternative. Okay, so let's figure out how we prove this property. The formal methods tool that we use to build the authorizer is called Daphne. It's a verification-aware programming language. And in Daphne, we're able to write down that formal specification, write down the code for the implementation, and carry out a proof that the second matches the first. And we're also able to prove properties about the specification. So looking at the Daphne version of our deny trumps allow policy side by side with the English, we can see that they match up pretty well. So the property, we term it a lemma, just like mathematics, because it's something we're going to prove, and we give it a name. And the lemma is parameterized over all policies, all sets of policies, and all requests. And we say, for all those things, if there exists a policy P inside the set of policies, and there's a statement inside of that particular policy P's statements, and the effect of that statement is deny, and the statement matches a request of interest, then when we evaluate that request against the policies, the final outcome is going to be deny. So what is this evaluate thing here that I just glossed over? Well, that's the functional specification. This is a property about the functional specification. So at a high level, this is what the functional specification for the authorizer looks like. It takes as a parameter a set of policies and a request, and it gives back an answer, which is either to allow or deny the request. And the functional specification says that if a policy that has a deny effect matches the request, we should return explicit deny. If instead the statement matches, the request matches a statement in a policy that's explicitly allowed, then we'll allow. If no statement matches the request at all in any policy, we're going to deny, and it's called an implicit deny. So looking at that logic and imagining it at a high level and thinking back to our property, it's clear why our deny trumps allow property holds. Because the first thing we do is we check whether any statement, deny statement matches the request. And if so, we deny immediately. We don't even consider the other requests. And this kind of argument, like the one I just made informally, can be made formally to prove that property in Daphne. Now, of course, where the rubber hits the road is the implementation. There's a huge amount of code compared to the specification, much of which I haven't shown you for either, that we need to show matches up. And you can see here on the right-hand side, I've hand-waved with a comment. There's about 2,750 lines of Daphne code that implement an efficient algorithm for carrying out authorization. And a key part here is this ensures, which says that the result of the implementation is going to match the result of evaluation according to the specification. That if we had evaluated the sequence of policies, PS, and the same request over in the specification, we would get the same answer that we're getting in the implementation. And because we're doing a proof, we know this is true for all sets of policies and all requests. And we can repeat this process for many other properties. Okay, so how do we do it? Formal methods has a long history, and here we are, a big tech company using formal methods for serious products. What got us here? So I'm going to give you a brief history about that. Formal methods sort of began as a discipline in the late 60s, and much of its development occurred in the 70s. This is when the mathematical interpretation of programming languages and automated theorem proving really got their start. And there was a lot of enthusiasm and a lot of hope that mathematically oriented software development would become a mainstream reality. Unfortunately, that didn't exactly happen. And in the 1980s, there was a bit of a winter where formal methods researchers went underground a bit and decided to continue to develop things, but maybe more outside of the spotlight. However, there were a series of wins, and through the 90s, up until a moment that I think was a really big moment in the history of formal methods, in 2006 with the release of the CompCert compiler. So this is Xavier Leroy, who's a researcher at INRIA, who developed this compiler. So the idea with the CompCert compiler is that it allows you to prove that compilation is always correct, that given a C program, for all possible C programs, the output assembly language that you get will always behave the same as the original C program would have if you'd sort of interpreted it directly. That sounds exciting. Hey, I have a proof of this compiler. It probably didn't generate a lot of press right at the time it came out. But a few years later, I think it really captured people's attention because a different research project called CSmith was published. This is a tool that aimed to find bugs in C compilers by generating random C programs, feeding them to multiple C compilers, and seeing if any of the outputs of those compilers disagreed. If I give it to 3 C compilers, the same program, and those compiled programs behave differently, assuming I started with a deterministic program, something's wrong. One of those compilers is incorrect. Now, the striking thing is that there were no bugs that the CSmith team was able to find in the ComCert compiler. And this was not for a lack of trying. They devoted about 6 CPU years to the task of doing so. And by contrast, they found hundreds of bugs in the mainstream GCC and LLVM compilers, and they even found bugs in those compilers with optimizations turned off. So this was meant to be the setting in which those compilers were really, really trustworthy, and in fact, that's the setting that like aerospace and highly secure critical industries were using, and yet that apparently was less precise, less secure than the ComCert compiler. Now, the ComCert story moves forward similar to the IM story that we saw. Once they had that proof of correctness, they were able to make changes to the compiler, adding more and more optimizations to it that they could then prove were correct. And by 2016, according to this chart, we can see ComCert was producing code that was nearly as fast as optimized 03 GCC. No bugs have been found in ComCert's verified code to this day, and only a handful of bugs have ever been found overall. So this is a really exciting success story. Now, we heard about Cell 4. That came out in 2009, was used in HACMs, has been used in many highly critical projects. The IFACS air traffic control toolset came out in 2011. In 2016, Microsoft researchers began Everest, which is a project to formalize and prove key cryptography protocols correct and secure. Everest artifacts are now running in Firefox, Linux, Windows, and Azure, probably as often as the IM authorizer. And in 2024, we have the release of that authorizer, and in that same year, the Cedar project. So lots has happened, lots of exciting results. What made them possible? If we rewind back to 1997, sort of at the tail end of that winter, we can see a paper by John Knight and his collaborators asking the question, why are formal methods not used more widely? And according to their research, there were 3 speed barriers at that time: non-trivial added development costs, the need for developers to understand difficult mathematics, and inadequate tool support. If we look to today, the landscape has changed quite a bit. There are many tools available for code proving. Isabelle Hall for Cell 4, the Rock Prover for ComCert, F-star for Project Everest, Daphne for the AWS authorizer, and these tools have been used in other projects as well. And there are other provers. Spark was used for IFACS. It is still used today. Lean is a prover similar to Rock that we use with Cedar. I'll tell you about in a moment. Gobra and Varus do verification for Go and Rust code. So lots of development, lots of tools, many of which are used in industrial settings. Proof development now occurs in your IDE. It's not just for users of VI or Emacs in the VI Emacs wars. You can find it in VS Code and other places. Proof checking is in your CI/CD. So when you make a pull request and you make an update to your code, proof that you have about the code is rechecked automatically. Core theorem proving automation is advancing rapidly. This is some of the technology that makes it possible to reduce the human effort in carrying out the proofs. So this chart is showing the results of a benchmark carried out in 2020 as part of the Satisfiable Modulo Theories solver competition. All of the lines here represent prior year competition winners. So the competition started in 2002, and then here by 2020, right, we had many winners. And what this chart is showing is running all of those historical algorithms on this year's hardware for this year's competition. So the difference in the lines is the difference in advance in the algorithms, not the advance in the hardware only. So if we pick one line on this chart, say at 600 seconds, all of the dots that are intersected are the number of instances that these tools could solve in that amount of time. So if I graph them in a more normal-looking way, you can see that there's an upward trend over time, a pretty dramatic one, in improving this technology. And this is not even considering the use of parallel and distributed SAT solving, and it's not considering the use of Gen AI, both of which offer further opportunities for improving automation. Nevertheless, there are still challenges, especially in applying this most rigorous and assured method of formal methods. It's still going to add development costs. It's still going to require developers to understand difficult mathematics. So how can we cope with these challenges? Well, the first way that we can see this challenge of developers needing to understand mathematics is that they will have to write proofs themselves. So this is some Daphne code, this lemma you can see at the top, that notation, where I didn't show you the proof of the lemma before. Unless it's a relatively simple lemma, oftentimes a developer needs to provide some hints to the automation to carry it out. And that automation can also introduce engineering challenges around what's called proof brittleness. And that's because SAT solving is an NP-hard problem. It's an intractable problem, as we like to say. And some important proofs are actually undecidable in the limit. You may have heard of the famous halting problem being an example of that. So in some ways, back to Alice, we're tackling impossible things here. And that means we have to use heuristics and take advantage of good structure and use cases to do it. And when we ask provers to do that, sometimes those heuristics are brittle. And inconsequential changes to your program might lead to the prover timing out where it used to confirm a result. And of course, today, if you're going to start using formal methods, you need to learn these tools, and you might have to help build them up because they don't have the same sort of developer community behind them as a mainstream programming language does. So this was sort of the landscape that we faced when we started the development of Cedar. Cedar, as I said, learned the lesson from IAM. We wanted to build with formal methods from the beginning. But we were aware of these challenges, and we were aware that we wanted to build an open source community around Cedar. Cedar is meant to be for customers, so we wanted to release its core code and definition, and we wanted a community to be able to contribute to it. And that community didn't necessarily have mathematical sophistication. They may not know a custom proof language if we were using that. They may not be interested in learning those skills, and yet we still wanted them to come on board and take advantage of Cedar and its design. So what we did was we built a formal method-centered methodology called verification guided development that aims to leverage formal methods in the most critical way, but to use some of those lighter weight formal methods that Kathleen hinted at in some of the other parts of Cedar's development. And the key is that I've learned is that by focusing on properties that you're trying to establish about your system, thinking about them right from the beginning, you can have significant gains, whether you're doing full-on proofs of those properties, or you're using a memory-safe language, or you're using something like property-based testing. So let me tell you more about that. If we look back at that picture I drew before about formal methods with an implementation, a functional specification, and properties, one observation we can make is that even if we don't prove the correspondence between all of these things, it's actually an excellent exercise to have gone about constructing them. I can't tell you how many times I've heard from people when they say, just by the virtue of writing the formal specification, we found 10 bugs in our system because it forced us to think carefully about what we wanted. And the same thing goes with thinking hard about properties you want your system to satisfy. Now, in addition to proving those properties, you can also test them, or you can use an automated reasoning technology that maybe is a little bit short of full proof, but is nevertheless doing some of that symbolic reasoning, such as symbolic execution or model checking. So that's what verification-guided development is about. It's about focusing on properties and about specifying what your system does, but then using a combination of proof and property-based testing to establish that the system does what you want. And this is what it looks like for Cedar. So we use that lightweight formal method, a memory-safe programming language, Rust, for building our production implementation. And that's what we open sourced, and that's what outsiders regularly contribute to. On that Rust code, there are a bunch of key components that we want to make sure do the right thing. So for example, we want to make sure that our parser and our pretty printer go in a loop. That if I parse in a Cedar policy and then I print it back out again, I get the same thing that I started with. Because if I didn't, then there's something wrong with either my parser or my printer. We also use differential testing to test that production code against a model. You can think of that as the specification that's written in the Lean programming language. And Lean is one of these verification-aware languages about which we can prove properties. So here we can specify properties like that deny trumps allow property and actually prove them in our model. By virtue of having done the differential testing to test that the model and the production behave the same, when we prove properties in the model, we have good confidence that they hold in the production code too. And using this methodology, we found dozens of design flaws, and we found them with all three methods, using the proofs, the differential testing, and the property-based testing. So just to say a little bit about what property-based testing is, since I've just used the phrase and not defined it, the idea is similar to what we saw before with the Daphne presentation of that deny trumps allow property. You write the property down, but you write it down in code, and then what you do is you generate many, many inputs. You use a systematic input explorer to run your production code on those inputs, and then to establish, ask the question, does the property hold or not? If the property does not hold, you've found a bug. If the property does hold, you've now thoroughly tested that your system satisfies it. It's no guarantee. Proof is always your best bet in terms of getting a guarantee that your system does what you want. But thinking in terms of properties allows you to test whether or not your first approach satisfies that property. And if eventually you take a proof-based methodology, you'll be able to find mistakes before you spend all kinds of time trying to do the proof. So if we step back and look at the trade-offs here, we can see that proof allows us to define our property in logic, and in property-based testing, or in differential testing for that matter, we define it as code. In that proof, we have to use that special proof language. For differential testing, we write input generators. In the proof side, the very most rigorous formal methods are harder to deploy. They're smaller pieces of code, and they're in more specialized environments and using specialized tools, whereas property-based testing can be applied to huge systems and has been. What we have here is a continuum. On the left-hand side, we have the highest assurance, but we require more expertise, and we have fewer opportunities for scalability and for deployment because of the state of the tools. But on the right-hand side, the assurance goes down while scalability improves, and it's easier to get started. And of course, we go the other direction. Now, a thing that I think is a really great approach, and one that we did in Cedar many times, is to property test a property first, and once you have a good idea that it's a sensible property, to then go and prove it. So we would property test things in our Rust implementation, and then when we were confident they were true, we would go off and prove them in the Lean model. And as I mentioned before, in between is technology like model checking, which we've used at AWS as well, which gives you a way of doing symbolic reasoning up to a bound. It's a more complete way of doing testing, in a sense, to establish that a property holds of your system. So here are the takeaways of my talk. Number one, you can use formal methods today. We are using formal methods to build our most scaled safety and security critical code, like the IAM authorizer, fully built and proved correct using formal methods. We've been using formal methods and techniques like model checking and property-based testing for years on a huge amount of code, and we're doubling down and doing more and more. Other companies are doing this too, like Microsoft and Project Everest, like Firefox taking on that cryptography code. It's available, it's ready to go. And Gen AI is making things easier. We heard about some programs that DARPA is exploring today to leverage Gen AI to make proofs easier to carry out. Another takeaway is that formal methods offers assurance, first of all, but agility as well. Because you have that proof and you have a process for reestablishing it, you have greater confidence to more quickly make changes like optimizations and feature additions because you're able to quickly reprove them rather than go through a long and arduous acceptance testing process. And finally, when considering that continuum of formal methods, having a memory-safe programming language with property testing is a way of getting started, of moving towards a property style of thinking that can take you towards formal methods while not reaching it right away. And a property is a statement that holds for all or many things, not just one. And by doing that, based on our Cedar experience with Cedar, you can catch many bugs earlier and attain higher assurance. And let me plug, if Cedar sounds interesting to you, it's open source, check it out. So I hope I've convinced you that formal methods is not a thing of the past or a thing that's out of reach, but something that is practical and that if we can do it at Amazon, you can do it too.